Okay, so we're going to look at free body diagrams number 2, and we're going to be, again, analyzing what are our interactions, what are our objects, and how do we take those interactions and our scenario and turn it into a free body diagram. So this daily practice has 4 different examples in it. I'll probably fit 2 for the first, and then we'll do a second recording for the last 2, depending on how much room we have. So just be a little patient with that. All right, the first scenario that we have to set up reads, you are rearranging your room and pushing the couch along the carpet. It's a shag carpet, so there's lots of friction. You're pushing the couch so that it is speeding up as it moves along the carpet. First thing we have to do, identify that object. So our object that we're interested in looking at the forces on, of course, is the couch. All right, so then as we move into analysis, pictures are going to start to be helpful. So here's our couch, I guess, sort of. And I like to add some reminders so that I know as I'm doing the analysis, I'm pushing it in this direction. So it's going to have a velocity to the right. I'm defining it to the right. And it's speeding up. So how will that define how our forces look? We want to be thinking about that and conceptualizing it as we move through. Okay, after our picture, we start to consider those interactions, what forces are involved in this problem, and those interactions develops those force trees, really defining them, telling me as your instructor what you know to be the 2 objects interacting in any forces. And as we do that, we can develop the free body diagram. Okay, so one force hanging out, working on that couch, interacting with that couch. And always the easiest one to do, of course, is the force of gravity. So 2 interacting objects. It's always the object that we're interested in is one of those objects. After all, that's what we're analyzing the forces on. And with the case of gravity, the other object is the Earth. So as you listen, as you go through these videos, pause them, put those forces down, re-look at them, do what you can to make the strategies work for you in how you use this tool. So gravity always acts down. So if I bring over my free body diagram, start to put those forces on it, and we have the force of gravity, which is a friendly reminder is mass times gravity, and also goes by the weight. Okay, another interaction. Well, couch is sitting on a surface, so we must have that molecule squishing interaction or the normal force, and that's going to be between the couch and the ground, or the carpet in this case. That's what the true interaction is with that carpet. It's being squished down, the carpet is, so it's pushing back up. And we have the normal force. Now, it tells us that the couch is being pushed along the carpet and speeding up, but it's not changing its motion up and down. And so as we start to develop this free body diagram, we might want to think about the lengths of our arrows relative to the situation. If it's not changing its motion up or down, we know the sum of the vertical forces are 0. Remember, we can separate them. We can look at vertical separate from horizontal. So our up arrows and our down arrows all have to match. And I didn't do that good of a job on that, but I want them to match, so we'll just make this arrowhead a little bit bigger. And now it looks as though the normal force and the force of gravity match better. They're intended to match. I dropped the marker head. Hang on. Okay. Any other interactions? Well, I'm interacting with it. I'm pushing it across the floor. And so we're going to have the force of the push. And that is between the couch and me. And I'm pushing it to the right. I defined that in the problem, so that's going to be to the right. So it has to show up on my free body diagram as the force of the push to the right. And then, last but not least, it tells us we have friction. So I have a frictional force. It's moving, so this is kinetic friction, and that is between the couch and the carpet. Friction opposes motion. If motion is to the right, then friction must be to the left. And now I can put it on my free body diagram. But again, I want to be careful. How do these arrows compare? It tells me that it's speeding up as it moves to the right. Moving to the right, speeding up to the right. Speeding up tells us the acceleration and the velocity are in the same direction. That means the acceleration is to the right. And if the acceleration is to the right, then the sum of the forces in the horizontal direction, that's the forces that the motion is in, has to be to the right. Now, if the sum of the forces is to the right arrows have to be bigger than the left arrows. I only have two. So relative to the right arrow, my frictional force, which is kinetic friction, should be smaller. Okay, so this free body diagram tells me that nothing's happening up or down. It's not changing its motion. But since my right arrow is bigger than my left arrow, and there's only two to worry about, there's a net force to the right. That means the object's accelerating to the right. If it's already moving to the right, it's speeding up to the right. Okay, so that's part number 1. Let's try number 2. Number 2 says you push a mug along the top of the counter as it slides to a stop. Draw the free body diagram and force tree after you let go. So after you have interacted with it. So we don't care about the push. We just care about the sliding to a stop. Okay, same process. We start with our object. Well, it's that mug. We're interested in what that mug is doing as it slides across the table. Pictures can often help us conceptualize, visualize what's happening. So here's our mug. It's moving to the right, so we know it has a velocity to the right. It's not a very good V. I will make that a little better. All right, so it's moving to the right, and it says it is coming to a stop. Well, that tells us that it is slowing down. So be thinking about, what does that tell us about the acceleration? Well, if it's moving to the right and slowing down, opposite. Velocity and acceleration are opposite. So the acceleration has to be to the left. If the acceleration is to the left, then the sum of the forces in that direction, along that plane, also has to be to the left. So that's going to help us as we develop that free body diagram. We're going to do a little more proactively this time around. All right. So let's look at those interactions. Okay, well, we have the force of gravity. That one's that easy one. So here's our force of gravity. That is between always our object and the earth. So as I start to develop my free body diagram, there's my mug. And the force of gravity is, and we know it's down. So the force of gravity is going to be down. And just as a reminder, that's mg times the weight. We're not using that information just yet, but it's going to help us remember to not make the very common mistake of just using m or just using g. And remembering that force of gravity is weight. Okay, that mug is interacting with the counter, squishing the counter's molecules, and they're pushing back. So we have that normal force between the mug and the counter. And if they're pushing back, they're being squished down. They're pushing up. Now, this mug is not changing its motion up or down, and so the net force up and down must not be anything, must be 0. And so as I think about what my ups and downs are going to do, is they're going to be the same length. Now, if I end up with more ups and downs than I thought at this point, I'm going to have to make an adjustment. But for now, I think those are going to be the only ones. They're meant to represent that same length. Okay, it says that I push the mug, but I'm interested in the motion after I let go of it. So I'm not interacting with it anymore. So I'm not going to have a force interaction that's in the direction of the mug, but I know there has to be a net force to the left, which means there has to be a force to the left, especially if there's no force to the right. And so our last force to consider is that force to the left, which must be friction. And the object is moving, so it's kinetic friction. That's going to be between the mug and the counter. And so it has motion to the left. Now, if I look at this free body diagram, what does it tell me? It tells me the object, if these two forces are the same, the object is not changing its motion up or down. Well, the mug isn't. It's staying in the horizontal plane along that counter. A force to the left tells me that the acceleration is to the left, a net force to the left. Nothing to the right, net force to the left. That means the acceleration is to the left. Well, if the velocity is to the right and the acceleration is to the left, the object must be slowing down. And indeed, the problem tells us the object slowed to a stop. And I can't come up with any other physical contact, physical interaction, or type of force that acts through a distance to add to my picture. So there's no more interactions. So that's the free body diagram of this mug coming to a stop. All right, we will do the second two in the next video, part B. Keep up the good work.